Hello. This class is focused on understanding how we can design process flow for MEMS based microsensors, and these sensors that we will be learning in this particular class would be used to understand or diagnose cancer. So, when you talk about cancer, we are focusing on tissue related cancer, okay, cancer that occurs in tissue. And to start with, we will talk about breast cancer. As we already know, breast cancer is second largest cause cancer related death. The second largest cause of cancer related death in women, not only in world but also in India, and that is why from clinical perspective this is very important disease that one needs to understand, and there are open ended problems that one needs to find the solutions for. So, when I say about open ended problems, that means the problems that about the diagnosis. It is not that we do not have cure for cancer, the only thing that we are lacking is a right time diagnosing of cancer. So, when we have a proper diagnosis, then we can go for a proper treatment. As an engineer or as a scientist, how we can come up with an idea or novel sensors that can aid the clinicians or a path lab to diagnose cancer at early stage, right. This is the focus. So, when we talk about cancer, in particular tissue related cancer, the tissue property changes as the cancer progresses. So, when I say about tissue property changes, what does that mean? If you have ever noticed a person suffering from cancer, he will start developing or she will start developing a lump, right. Not every lump is cancer. For example, if it is it can be just a benign lump, it may not be cancerous lump. There are fibroids that develops and the fibroids may not also always turn into cancer. Now, but the point is that whenever there is a lump, what we feel or what a patient feels is that there is a stiffness. Right, there is a change in the stiffness. So, in case of breast cancer, if there is a formation of lump, that particular lump will have different stiffness compared to other area of the breast. So, one thing that we understand from this particular stiffness is that we can design a sensor that can be used to measure the stiffness of tissue. So, stiffness of the tissue or elasticity of the tissue can be one of the parameter to understand or to diagnose cancer at early stage, right. So, we will try to see how we can understand this particular tissue related cancer. To do that, if we see the slide, what we see is we are looking at the gold standard. Gold standard in case of breast cancer is to go for MRI and mammography, and if the MRI confirms there is a suspicious region, right. You can see here there is suspicious region, here also there is a suspicious region, then the clinician would ask for the biopsy. Biopsy is you have to take the tissue out and then need to understand the tissue properties. Alright. So, in this case, once the tissue is out, it is sent to the path lab where they look for different markers HNE, P63, estrogen, postrogen, there is also called marker called HER, right. And then using these markers, biomarkers, right, and the final conclusion or final diagnosis would be a patient is having cancer or patient is not having cancer, right. In this particular case, in this particular techniques, there is one drawback, and that is that there are a very high number of false positive and false negative results. So, how can we reduce this false positive and false negative result? That is our goal, alright. So, first thing that we will learn in this particular topic is, can we understand the stiffness of tissue, right. So, you see that if the tissue is taken out, right, from the biopsy, when the tissue is taken out, it is sliced into several parts. You can see here, this is for immunohistochemistry and spatial staining, this is for SEM analysis, and this is we can use for our experiment, which is our MEMS experiment. alright. And when you look at the tissue, the morphology of the tissue is also different. You can see the surface morphology of this tissue, whether it is stromal tissue, whether it is epithelial tissue, right. If it is a cancerous tissue, the morphology would be different. Here you can see, if the normal tissue, morphology is different, right. So, from the morphology itself we can see that there is some difference in the tissue properties, right. So, how can we now measure the stiffness of tissue? So, once the slice is out, the slice is kept on the microgrid, as you can see here. This microgrid is nothing but a mesh. If you have seen mosquito mesh at your home, similar to mosquito mesh, but it is extremely micron in dimension. That means that the width and the spacing of this mesh, the lines are the width is about micron and the line spacing is also about few microns. So, this is a mesh and is called microgrid on which we can place the breast tissue, and then we will see what kind of tool or a device can be used to measure the stiffness. So, if I go to the next slide, we will see what are the what is that device. But before I move to the next slide, let us see one more thing in this slide is that a woman of all ages, women of all ages are encouraged to perform breast self exams at least once a month. Okay. Once a month every woman is encouraged, or are, if it is women, are encouraged to perform breast self exams. While women in the age of 40 to 54, every year they should go for mammography, while those who are 55 and above should go every 2 years once for mammography. Alright. So, this is something that is required as an awareness, We are not aware of diseases, we are not aware of things around us, and that is why there are large number of deaths. So, if you are learning this particular subject, also try to aware the people around you, your loved ones, your relatives, your friends, and understand this kind of diseases, so that more we understand, more we are aware, less number of deaths will happen around us. Alright. So, awareness is very important along with understanding engineering and creating new devices, but if you are not aware, then we will reach to a stage that already cancer has been at that particular stage or final stage, that it is very difficult to cure the patient. Right. So, when I talk about awareness, is just like what kind of program, what kind of screening methods that are available in market that we can use to understand the wellness for our body. Right. Everything is working well within our body, there are programs available to understand those things. That is what I mean by awareness. So, when we go to this particular slide, what we see is, we see a piezoresistive micro cantilever. What is the role of piezoresistive micro cantilever? The cantilever, the role of a cantilever is just to if we are using it in AFM, if we are using it in AFM, it is called atomic force microscopy, then its role would be to let us know the surface roughness of the film. If the cantilever is integrated with a piezoresistor, you can see here, if a cantilever is integrated with a piezoresistor, then whenever there is a strain in the cantilever, whenever cantilever bends, there will be strain in the cantilever, and this strain will cause change in the piezoresistive material. So, the piezoresistivity would change depending on how much force we are applying to the cantilever, and we can measure this by change in resistance. That means, if I measure the resistance across these two pads, right, depending on how much my cantilever is bending, there will be strain induced into the piezoresistor, and corresponding to this change, to this strain, I would see the change in the resistance. Right. So, the point is how we can create this piezoresistive micro cantilever, and how we can use this to understand the surface or the tissue properties, surface of the tissue or the tissue properties. right. So, as you see there is this is a top view, is an optical photograph, this is an SEM image, these two are SEM images, and this is a chip, there is one single chip. At the end of this chip, which you cannot see, there is a cantilever. This is not visible with a naked eye, so this is fine, alright. So, what is there on the tip? And the tip of this cantilever, as you can see, there is an SU8 material. This tip is made up of SU8. Here you can see here SU8 tip, right. So, what is SU8? SU8 is nothing but negative photoresist. SU8 is a negative photoresist. We have seen photolithography, and in photolithography we have seen there are two types of photoresist. One is positive photoresist, second is negative photoresist. SU8 falls under the category of negative photoresists, right. There are several advantages of using SU8, and that we will discuss later on. Right now just focus that you see there is a tip, there is a cantilever, this cantilever is completely released. You can see that the back side of the cantilever is not anymore connected with the silicon wafer. This is a silicon wafer, you can see all the lines, right. So, this cantilever is completely released. Okay. Now, there is a piezo resistor embedded within the cantilever, you can see here, right, embedded within the cantilever, and the thickness of this cantilever, is about 4 to 5 microns. The thickness of SU8 tip is around 10 microns. 10 microns. Okay. Now, you can see here this cantilever is also completely released, but there is a bend in the cantilever. You can see this bend, right. So, why this bending occurs? What is the why this cantilever is bent? And the cantilever that you can see on the left side is not bent, it is straight. That is the first question. Second question, how we can embed the piezo resistor, alright. Two things we right now understand, that there is a piezo resistor cantilever, one is a straight cantilever, second is a bent cantilever. And this role of cantilever would be to understand the tissue properties, to understand the elasticity of the tissue. Okay. We will see how. So, now on the screen what you see is a piezoresistive microcantilever schematic diagram, where the probe tip, the thickness is written, radius is written, right, cantilever beam is there is a piezoresistor, its dimensions are given, right, and then there is a contact pad. This is the contact pad through which we will measure the resistance. Okay. This is a piezoresistive cantilever, another piezoresistive cantilever, where you can see it is completely released, and there is a piezoresistor embedded onto the cantilever. Now, how can we embed or how can we integrate the piezoresistive material or piezoresistive sensor in the cantilever beam? Alright. So, to do that we will start with a wafer that is called SOI. SOI. It is silicon on insulator. So, what does that mean? You see, this is silicon, right? This is silicon. This green thing, green line is what? Silicon dioxide. And on the top of this green line we again have silicon, right. So, this looks like this top silicon is on the oxide material, that means silicon on insulator, insulator is our SiO2, silicon is the top silicon. So, you can see that the silicon on oxide or silicon on insulator, right, this is our starting substrate, right, and there are several process flow, there are several steps, there is a process flow, there is a step to reach to this particular piezoresistive cantilever. What are these steps? What are these steps? Let us see. On the before we go to the next slide, let us see this particular diagram, which is on the left bottom. You can see that there is a SU8 tip cantilever to be released. You can see this is not released right now. It's you can see the oxide. You can see oxide surface of SOI wafer, right. Then there is a silicon nitride, and then there is a silicon nitride on SOI. In this particular area, silicon nitride is etched. Silicon nitride etched for releasing cantilever, right. This everything is written over here, and there is a role of silicon nitride in this particular piezoresistive cantilever, right. The silicon nitride role is to compensate the stress due to the silicon oxide film. The role of silicon nitride is to compensate the stress that is obtained due to silicon dioxide film. So, how does it work? How does this work? Now, this is our first step, we took SOI wafer. Second step is we are growing silicon dioxide, right. See here there are some colors given, so that we can understand what each color represents. The first one, that is purple in color, shows silicon nitride. Next one, which is green in color, shows silicon dioxide. Next one, which is gray in color, is called silicon. Next one is gold, is about gold in color. Then yellow is boron resistor, blue is cross link SU8, and orange kind of stuff is boron contact. Okay. So, our second step is to grow oxide on SOI. First step is SOI, sorry. Second step is oxide, that is our SiO2 on SOI, right. Third step is to create a window. Create window in oxide, right, top layer oxide. You can see here the window is created. How this is created? Using photolithography. We all know what are the steps in photolithography. First is spin coating. Spin coating of what? Photoresist. Second step is soft bake. Third step, mask alignment and exposure, UV exposure, right. Next step, photoresist developer. Next step would be hard bake, right. And next step would be you etch whatever the material, perform etching of the unwanted material, and then finally you strip photoresist. Stripping of photoresist is done using acetone, right. These are steps for photolithography, we already know. Using these steps, what we have done? We have created a window in silicon dioxide. So, once the window is created in silicon dioxide, what is the next step? Next step is you diffuse boron resistor, right. You diffused boron resistor. That means the step that you have created, if you see the top surface looks like this. This is the top surface. Which one? Point number 3. Here, this one. Next is we are diffusing boron, because only this area oxide is not there, right. you can see here only in this area where I am drawing the pattern the oxide is not there, in remaining area there is an oxide. So, we are diffusing boron in this particular area, that is why we say boron resistor, boron resistor. That is why we have shown by yellow color, right. Next step, what is the next step? Next step is we grow silicon dioxide. We grow silicon dioxide on this particular resistor, and next step would be create window in silicon dioxide for boron contact, for boron contact. You can see, right, after this, after growth. So, this is our fourth step, right. We have created a window, then we have created an oxide, and now we have created a window for the boron contact. Next step would be diffuse boron contact. So, if you see how it will look like, there was a resistor, right. Now, only this area is open. Okay. You can see I am deliberately drawing something. What you can see, there is oxide here everywhere except this area. You see this area that goes in, right. So, if I diffuse boron contact, this boron contact will overlap boron resistor only in this particular area, right, only in this particular area. Thus, we will have a contact to the resistor through the boron contact. We will have contact to the resistor through the boron contact, right, and the boron concentration for the contact region is higher compared to the boron concentration of the resistor. That is because we need to finally get a gold contact on the boron contact to form the ohmic contact, right. On this we will have a ohmic contact, we will see. Next step would be, next step is you deposit, next step is deposit chrome gold and pattern it. So, here what we are getting? We are getting a long contact pad out. So, where are we? You see here this contact pads. So, if you see I am drawing here, it goes all the way here, come back here, here, and then this particular box. Same way in this area it goes here, goes here, goes here, comes here, and then like this, right. So, this particular, the one that I have drawn with red is the one that we are right now on, which is point number 8. Next step is ninth step. Ninth step, as you can see, we have, ninth step would be, we have deposited or grown silicon nitride. You can see here ninth step, deposited or grown silicon nitride and create window, and create a window. You can see here, right, where we have grown silicon nitride and created a window. Step number 9. Okay. Now what? Next step would be you etch silicon dioxide and silicon. All right. So, 10th step. So, I am just rubbing it down the first 4 or 5 steps. So, what is my 10th step? 10th step is H. Can you see? Okay, let me go down so you can see clearly. Is it better? Okay. H silicon dioxide and silicon, right. Now, the question is, when should I stop etching silicon dioxide and silicon? Now, you see below silicon dioxide and silicon. So, first we have to etch silicon dioxide, then you will see silicon below it. When you etch silicon, you again see silicon dioxide below it. But when you did the wafer in silicon, you do not have to worry when it can be stopped, because silicon dioxide will act as a mask or etch stopping mask for silicon, because you see silicon dioxide will not be affected in silicon etchant. Okay. So, that is the next step, which is the etching of silicon dioxide and silicon. What is the next step? Next step is SU8 deposition or SU8 coating. We cannot deposit, coating and patterning for forming tip, right. SU8 spin coating and patterning to form the tip, right. Next step, I think this is number 10, 11, 12. Yeah. Next step, what is the next step? Create window on the back side of the wafer. Where we have created a window, you see here we have created a window where we want to etch silicon completely and release our cantilever, right. We have created a window where we want to etch our silicon completely and create a cantilever. Which silicon? The silicon which is the base silicon, not the silicon which is grown on insulator, because silicon which is grown on insulator will help to form the cantilever. Alright. So, create a window on the back side of the wafer. Okay, fine, we have created. Now what? So, to create this you have to understand that when we create it, we have to remove silicon nitride followed by silicon dioxide. We have to etch silicon nitride followed by etching silicon dioxide. Last step in this particular case would be to etch silicon. Right. We can use DRI to etch the silicon. DRI is your deep reactive ion etching, Okay. So, this is step number 13. So, what we have seen is, after following 13th step, we are able to release our micro cantilever. And another thing that we have observed is, we are using boron as the piezoresistive material, and the silicon that is on insulator is our polysilicon, or it can be single crystal silicon. The point is that you can also grow silicon on insulator and perform the experiment and evaluate its performance by or with the cantilever that you can make using silicon on insulator, which is single crystal silicon. Okay. So, piezoresistor is formed by diffusing boron into the polysilicon material or single crystal silicon material, and this will result in a creation of a cantilever, or let us say this my hand is a cantilever, creation of a cantilever with a tip, right. So, if I now use the cantilever in this particular fashion, right, and I press the cantilever on a surface, what will happen? The tip will touch first. Which is this tip? SU8. When it tip touches, my cantilever will move depending on how hard the surface is, right. How hard the surface is, this is my surface, this is my cantilever, I am holding my cantilever in this particular fashion. So, SU8 tip that was on the top, now it is at bottom, right, and now I am pressing the cantilever against the surface, and depending on the surface my cantilever will bend, right. So, this is the phenomenon. Now, when it bends, there is a piezo resistor embedded in the cantilever. When the piezo resistor is embedded within the cantilever, what will happen? There will be change in resistance based on how much is the bending of the cantilever, because based on the bending of the cantilever there will be a strain that is induced in the piezo resistor that will cause change in resistance. So, what we understand that now from here, if I instead of having the surface, I have a surface which is again hard surface on which if I place a tissue. So, if I have a place a tissue on this surface, what will happen now? Now, if I press the cantilever, depending on the stiffness of tissue, my cantilever will bend, right. So, this change in resistance will correspond to the tissue stiffness, right. This is how we can measure the stiffness of the tissue. So, if you see here in the next slide, what we have done? We have got the slice of the tissue, right, the slice from the benign region, slice from the tumor region. So, just understand this, if the cancer is somewhere here in this area, okay, and this is a tissue, this whole thing is a tissue, cancer is in this area. So, this area is cancerous, this area is not called normal, it is called benign, alright. So, it is not cancer, but it is benign. Okay. When you slice the tissue, you can go for IHC, you can go for mechanical characterization, that means understanding the stiffness. You can go for H&E image, and you can go for FESEM or field emission scanning electron microscopy. FESEM is field emission scanning electron microscopy. Alright. This is a simple electronic module that we can use, where your piezoresistive microcantilever is given by PMC. It is connected in a voltage divider fashion, which you can see right over here, and correspond. So, if a voltage is plus 5 volt, my output here would be 2.5 volts. That 2.5 volts I am applying to LM358, followed by sensor that finally shows display on my system, right. This is just one method. There can be multiple methods to use a signal conditioning circuit along with a sensor. The disadvantage here is that already we are down to 2.5 volts. So, our range of change is extremely small. If I do not have this, and if I have a Wheatstone bridge, I will have a probable better signal conditioning circuit. But that is not idea which kind of circuit you can use. You can always use a better circuit. The idea is that if I now have a piezoresistive microcantilever, and if I press it against a tissue, how can I see the change in the resistance or change in the voltage, right. So, you can see here initially it is close to 2.5 volts when both the resistors are balanced. That means, whatever the resistance of the piezoresistive microcantilever is there, same resistor I will use it here, the value of the resistor would be same, and then initially what I will have, because of the potential divider, I will have a voltage of 2.5 volts. As I go on pressing my cantilever, you can see here 0, 5, 10, 15, 20 microns. When I press my cantilever, I will be able to see the change in voltage, because there will be change in resistance, and that change in voltage will depend on what kind of tissue I am using, right. So, there is a benign epithelial and cancer epithelial. You can see benign epithelial and cancer epithelial. You can clearly see that the benign epithelial has a different range compared to the cancer epithelial. Same way, if I consider a stromal region. So, cancer can occur in epithelial region, cancer can occur in stromal region. If I understand stromal region, then you can very clearly see that benign stromal and cancer stromal, there is again a difference. Same way, if I take about second patient, you can again see that the cancer is different than benign, cancer is different than benign. Right. So, from here I can understand that my this change in resistance can show me whether the tissue is cancerous or not, because the cancerous tissue would show a different change in voltage compared to the normal tissue or benign tissue. Right. So, what we have learned until now is we can develop a piezoresistive microcantilever to understand the or study the mechanical property of tissue. Now, the question is, if I can study mechanical property of tissue, can I study electrical property of tissue? And if I can study electrical property of tissue, can I study other modalities like thermal property of tissue? Right. So, because if I can understand the stiffness of the tissue, then I can understand the change in resistance of the tissue, then I can also, if I change the resistance of the tissue I know, then I can understand the thermal conductivity of tissue. So, we are going towards measuring the electrical, mechanical and thermal property of tissue, but this is the first step where we are understanding the mechanical property of tissue. Right. The next step would be how we can measure the electrical property of tissue. So, that thing where we will look at the electrical property of tissue, we will see in the next module of the same lecture, and then the question is also that if I can measure mechanical, if I can measure electrical, can I measure mechanical and electrical together? You see, there is a never ending quest, because now if I can do mechanical and electrical, can I also do thermal? That means mechanical, electrical and thermal together, right. So, if once I have a chip which has a mechanical, electrical, thermal, what will I do and how can I operate this chip, how can I use this chip to diagnose cancer, right. So, with that we will see across this particular lecture series. So, just go through the this particular module. It is a short module where you will understand how we can design a process flow for piezoresistive microcantilever, and this piezoresistive microcantilever can be used to understand or to delineate between the benign and cancer, also to delineate between epithelial and stromal lesion, right. So, till then you take care, I will see you in the next module.